we're going to verify that the asymptotes of the hyperbola given by x squared over a squared minus y squared over b squared equals 1 are y equals plus or minus b over ax. We're going to do this by considering that as x approaches infinity, the distance between the hyperbola and the asymptote should become 0. That distance being the vertical distance, and so what I'd like to do, since I have the asymptotes equations in terms of, y in terms of x, I'd like to solve the hyperbola's equation for y as well. Our first step is to isolate the y squared term. We end up with y squared over b squared is equal to x squared over a squared minus 1. And so that y squared is equal to b squared times the quantity of x squared over a squared minus 1. Pulling out a denominator factor of a squared, we get b squared over a squared times x squared minus a squared is equal to y squared. Finally, square rooting both sides gives us y equals plus or minus b over a times the square root of x squared minus a squared. For our purposes right now, we will use the positive version of that. And we're going to look at the limit as x approaches infinity of b over a times the square root of x squared minus a squared minus b over ax, which is the expression that we have said defines the asymptote. Well, as x approaches infinity, b over a is a constant. And so this is going to equal b over a times the limit as x approaches infinity of the square root of x squared minus a squared minus x. You may recall from finding limits before that when we have a square root and another term, oftentimes we will multiply by a conjugate. And so we are going to multiply numerator and denominator by the square root of a squared minus a squared plus x. And as I said, numerator and denominator. So that ultimately we're multiplying by 1. Simplifying that product gives us b over a times the limit as x approaches infinity of x squared minus a squared minus x squared over the square root of x squared minus a squared plus x. In the numerator, the x squared is subtract out. And now, folks, as x approaches infinity, because we have factors of x in the denominator that are added together, we're going to end up with a denominator of infinity plus infinity. The limit here is 0. Therefore, as x approaches infinity, the difference between the expression that gives us the hyperbola and the expression that gives us the asymptote is 0. You would find similar results with the various iterations of plus and minus you see here. I encourage you to play around with that a bit. Now again, hyperbolas are one of the conic sections. And what we have here is a cone. And this is the first time that we care that a cone has two napes. Actually, there's the upper part and then there's the inverted part. And if we slice the cone, both in such a way that both napes are sliced is really what it is, then the shape that we get is a hyperbola. And that's why hyperbolas have two branches. The fact that we're slicing a cone in this way makes for a very interesting place to see where hyperbolas show up. Here we see a picture of a jet breaking the sound barrier. And you can see the waves of wind, air, are collecting. And folks, they're doing so in the shape of a cone. So if we would take this picture of the hyperbola and rotate it, then essentially this part of the cone is this sound wave here, this disturbance that the jet is causing. And this path, this curve would be essentially the ground. So you've got a cone that's intersected by the ground. And the way it works is everybody who's standing along that hyperbolic curve will hear the sonic boom at the same time. We've talked in other videos about the strength properties of parabolas and ellipses. And there are also strength properties with hyperbolas that make them useful in building. These are actually cooling towers for a nuclear power plant. And the shapes that you see here on the edges are parts of a hyperboloid, is what it's called. They're just chopped off at distances that aren't the same as each other from the center. So the center might be, somewhere right here. And then this next picture is not necessarily related to a property of hyperbolas in terms of the sound waves or the strength properties, but hyperboloids show up in gears sometimes. And these are referred to as gears with skew axes. And the shape of the gears themselves are hyperboloids. And so when we say skew axes, they're not parallel, they're not perpendicular. And it's just something that somebody figured out at some point. Hey, if we create a gear that's in the shape of a hyperboloid, then we can have things causing one another to spin when their axes are at odd angles to each other.